Hello and welcome to this lecture series on ordinary differential equations. In the last lecture, we talked about the definition and formation of ordinary differential equation. In this lecture, we are going to talk about how to find out solutions of ordinary differential equation. And in particular, in this lecture, we will talk about the first order and first degree ordinary differential equations. So, the general form of the first order and first degree ordinary differential equation is dy by dx is equal to f of x y. Okay, so we are calling this as a first order first degree ordinary differential equation because in this differential equation there are two variables x and y is acting as a dependent variable and x is acting as a independent variable. So there is only one independent variable in this differential equation, so it is ordinary, and there is a derivative term and it is equation, so differential equation. The order is 1, okay, first order, because the highest derivative is dy by dx, and degree is 1 because the power of dy by dx is also 1. Okay, this differential equation may be linear or non-linear depending upon how this function f of xy is defined. Okay, the left hand side is dy by dx. Here this term dy by dx is a linear term because the dependent variable y is occurring only one time, but on the right hand side it is a function of xy. So depending upon how this y behaves on the right side, this equation may be linear or non-linear, right? Now for the differential equations may have analytic solution, and sometime it is not possible to find analytic solution, so in that case we can find the solution numerically. Okay, but to start with, we are only concerned with how to solve a ordinary differential equation analytically, how to find a analytic solution of this. Okay, so for the first order first degree differential equation there are some standard forms, and those standard forms can be solved easily to find a analytic solution. Okay, so the first standard form is known as the variable separable form. Then we can have homogeneous differential equations, so first order first degree, or linear differential equations, and exact differential equations. So they are the standard forms. These four types of standard forms for which the analytic solutions are possible. So today we are going to discuss this first form, which is variable separable form. And if you are given a first order first degree ordinary differential equation which is in the variable separable form, then how we can calculate the analytic solution of this differential equation. So variable separable form, as the name suggests, there in a differential equation first order first degree, we said that we have two variables x and y, right? And so variable separable form. Okay, so how we can separate the variables? That means there are two variables x and y. So if we can write the variable x on one side of the equation and variable y on the other side of equation, then they are variable separable. Okay, so if in an equation it is possible to collect all the functions of x and dx on one side, so that is one variable, and all the functions of y and dy on the other side, so that's the second variable, then the variables are said to be separable. Okay, so the general form of this equation can be written as some function of y dy is equal to some function of x dx. Okay, so phi y dy is equal to psi x dx. So this is clearly a variable separable form because the variable y is on one side and x is on other side of the equation. So variable y is separated from the variable x. Okay, so if you can separate the variables from the differential equation and take one variable on one side of equation and second to the other side of equation, then you can simply integrate on both sides to find a solution of it. Okay, so integrating both sides, we get that the integral of left hand side equals integral of right hand side, plus we'll add a constant of integration, so it c is the arbitrary constant. Okay, and this is the general solution for the differential equation. Okay, so given a first order differential equation in first degree, and if you can separate the variable, then integrating and adding a constant of integration, this will be the solution of the differential equation. Okay, and this is a general solution because the first order differential equation, this equation has exactly one arbitrary constant. Say for example, given this differential equation, and say we have to solve this, dy by dx is equal to exponential function of 3x minus 2y plus x square e power minus 2y. Okay, so this is a first order, first degree, because the highest derivative is dy by dx and the power is 1, and on the right hand side you have some function of xy. Okay, so we have to solve this differential equation. Okay, so your first idea is to see what is the order and degree, right? This is the first order, first degree. Then see whether the variables can be separated or not. Okay, so on the right hand side, can you separate x and y? Okay, if it is possible, then you can easily rewrite this equation. Okay, so you can see that e raised to power minus 2y is here, and e raised to power minus 2y, so you can take e raised to power minus 2y outside, and inside we will have e raised to power 3x plus x square. Okay, so then you can take exponential 2y to other side and take dx from here to right hand side. So this equation can be easily written as e power 2y dy is equal to e raised to power 3x plus x square dx, right? So y variable is on one side, x variable on the other side, variables are separated, so you next step is that you simply integrated both sides. Okay, so integrating both sides, so integral of left hand side, integral of right hand side, and adding a constant of integration where this is a arbitrary constant. And so we know the integral of this e raised to power 2y dy is e raised to power 2y by 2. Similarly, exponential function e raised to power 3x over 3, and integration of x square is x cube by 3. So you can simply integrate this, and this is your general solution for this differential equation, right? So it's very simple to solve once you recognize that you can separate the variables. So I take another example, say solve the differential equation xy dy by dx is equal to 1 plus x plus y plus xy. Okay, so again you find out the order and degree. Okay, so highest derivative is dy by dx, first order, its whole power is 1, so first degree. Obviously it is non-linear because it is a y times y. Okay, so non-linear differential equation, but you see that we can again separate the variables here. If I take y common from last two terms, then it is 1 plus x, and then 1 plus x can be common, so that means right hand side can be written as 1 plus x into 1 plus y. Okay, so I can easily take y on one side of equation and x on the other side of equation. Okay, so this equation can be written as y over 1 plus y dy is equal to 1 plus x over x dx. Okay, now once the variables are separated, then you integrate both sides and add a constant of integration. Okay, so integral of this equals integral of this plus constant. C is arbitrary constant, right? So integral of this is you add 1 and subtract 1, so 1 plus y over 1 plus y is 1, that's integral is y, minus 1 over 1 plus y, so that integral is log of 1 plus y. 1 by x integral is log x, and x by x is 1, so integration is x. Okay, plus c, and then you can rewrite this equation, combine these two logs. Okay, so you can simply rewrite y is equal to x plus log of x 1 plus y plus constant. This is the general solution of the differential equation. Okay, it has arbitrary constant exactly 1 because the order is 1. So take one more example here. Say consider the differential equation 3 e power x 10 y dx plus 1 plus e power x secant square y dy is equal to 0, given y at 0 is pi by 4. Okay, so there is a condition given, say initial condition, so you can call it a initial value problem. Okay, so again it's a differential equation. If I divide with dx, then dy by dx is the highest derivative, so first order, first degree. So to solve this, again you can see that easily we can take y on one side of equation and x on the other side of equation. Okay, so 3 e power x divided with this x1 plus e power x dx, take this to other side, secant square y dy divided by 10y. Okay, so the variables are separated, so you simply integrate on both sides and add a constant of integration. So right, integrating both sides. So this is simply 3 times function this, and the numerator is the derivative of denominator, so it is log of 1 plus e power x. Similarly, derivative of 10y is secant square y, so integral of this is log of 10y. Okay, so this is 3 times log, and then because of log it goes to power. Okay, and then I can combine log terms to rewrite the solution as 1 plus e power x cube 10y. Okay, this goes to other side and logs are combined, is equal to c1, where c1 is after taking this anti-log, so c1 is another arbitrary constant. Okay, or you can also write here e power c. Okay, so where this is the general solution of the differential equation. Now we can utilize this initial condition which is given, that at x0 y value is pi by 4. This condition will be used to calculate this arbitrary constant. Okay, so and given y0 equal to pi by 4, so we can substitute x value 0 and y value pi by 4 here, and that you can calculate c1. So when x is 0, it is e raised to power 0 is 1, so it becomes 2 cube 8, and tangent of pi by 4 is 1. So c1 value equal to 8 we can calculate, and then we can substitute it back here to write that the solution is 1 plus e power x whole cube 10y is equal to 8. Okay, so this solution do not contain any constant value is substituted as 8. Okay, so this is a particular solution of the differential equation, right? Now, there are certain forms also which we say that which are reducible to the variable separable form, and the form is this: dy by dx equals to function of ax plus by plus c. Okay, so it's a first order, first degree differential equation where there is a function of ax plus by plus c. So this is not a variable separable form, but by using a suitable substitution this can be reduced to a variable separable form. Okay, so in this case the substitution is ax plus by plus c as a new variable, say t. Okay, so if we substitute ax plus by plus c is equal to t, then this right hand side becomes function of t. Okay, and this dy by dx we can calculate from here and substitute. Okay, so if I differentiate this with respect to x, so this will be a plus b times dy by dx, derivative of c with x is 0, and dt by dx. Okay, so this, so I can calculate dy by dx from here as dt by dx minus of a divided by b. Okay, so 1 by b derivative minus a, so that value of dy by dx we can substitute at the left hand side, and this ax plus by plus c as t. Okay, so this differential equation can be written as dy by dx substituted as this on the left hand side, so 1 by b dt by dx minus a, and equal to right hand side becomes f of t. Okay, this whole term is t. Okay, and then I can take b on other side, take a on other side, so dt by dx is b times ft plus a. Okay, and this whole term if I divide on other side and take x on other side, this is a variable separable form. Okay, I can take t on one side of equation and x on other side of equation, so I can easily write it as dt over b times ft plus a is equal to dx. So variables are separated, right? So now once variables are separated, we know how to solve this. You simply integrate it on both sides, add a constant of integration, and that will be a solution, right? So if you have equation of this form, okay, where there is a function of ax plus by plus c, okay, linear in xy, then you can substitute this as a new variable. It will reduce to variable separable form. Now we can integrate this to find a solution, and once we have solution we need to use a back substitution for t. Okay, because it will give a solution in variable x and t, and then we can substitute t as ax plus by plus c to find the solution of this original differential equation. Okay, say for example, say we have to solve dy by dx is equal to 1 over x plus y plus 1 whole square. Okay, so it's a first order, first degree non-linear differential equation and the variables are not separable here. Okay, we cannot do x on one side and y on other side of equation, but it is of form dy by dx is equal to function of ax plus by plus c. Okay, this ax plus by plus c occurring here. Okay, so if I substitute this as new variable t, I can reduce it to a variable separable form. Okay, so here substitution is x plus y plus 1 is equal to t. Okay, so if I use this substitution, x plus y plus 1 is equal to t, and then if I differentiate this with x, then 1 plus dy by dx is dt by dx. So I can also write dy by dx as dt by dx minus 1. So substituting this on left side and this on right hand side, the differential equation can be written as dt by dx minus 1 is equal to 1 by t square. This is t quantity. Okay, so 1 by t square, and then I take 1 on other side, take LCM. So this is a variable separable form. I can easily rewrite this to separate the variables t on one side and x on the other side of equation. Now once the variables are separated, I can simply integrate on both sides and add a constant of integration. So the value is, in after integral, t minus this is tan inverse t is equal to x plus constant. Okay, so I can integrate this to find the integral of 1 is t, integral of this quantity is tan inverse t, integral of 1 is x with dx plus constant of integration. So it's a general solution with the variable t and x. So I need to use back substitution for t, and t is x plus y plus 1. So the solution becomes y with x cancels out, so y minus tan inverse x plus y plus 1 is equal to c minus 1. So this is a general solution of the original differential equation, right? So I take one more example here. Solve the differential equation dy by dx is equal to sine square x minus y plus 1. Okay, so again it's a first order first degree differential equation, and the variables cannot be separated, but it is of form dy by dx is equal to some function of ax plus by plus c, right? So if I substitute this x minus y plus 1 as new variable t, then this becomes sine square t. Okay, and so I can easily separate the variables. So we will substitute here x minus y plus 1 is equal to t, so that if I differentiate this with x, it is 1 minus dy by dx is equal to dt by dx. So I can substitute dy by dx as 1 minus dt by dx on left hand side, right hand side is sine square t. Okay, so it becomes a variable separable form. Okay, I can rewrite this, take dt by dx on other side, sine square t, cos square t. So take t on other side, x on other side, so 1 by cos square is secant square, so secant square t dt equal to dx. Now its variables are separated, so integrate both sides and add a constant of integration. So we have solution as tan t is equal to x plus c. So variable t is back substituted as x minus y plus 1. Okay, so that gives us the general solution of the original differential equation, which is tan of x minus y plus 1 is equal to x plus c. Okay, so that's the general solution of this differential equation. So this was the variable separable form for the first order first degree differential equation. In the next lecture we will talk about the second form for which analytic solution is possible, and that form we will talk about is homogeneous equations or homogeneous first order ordinary differential equations. Have a good time.